Hi, it's Robin. My patron grymmjack wanted to know how he can achieve a sleep or a wait command in BASIC so you could just stop execution for, say, 1 second and then resume. Okay, well, I can think of maybe 3 different ways in BASIC to do that. So let's take a look at them. Probably the simplest way is just to do a for next loop, like for I equals 1 to 1000 next. And if we run that, it takes about 1 second to execute, and then you see we're back at the ready prompt. Now, if we want to benchmark this, we can just add line 10 in front where we set the TI string variable, this is a system variable for the time, to 0. And then we can print the TI variable without the string, which returns the number of jiffies, that is 60ths of a second. And we can actually divide it by 60 to return the time in seconds. So if we list that program, you'll see the line that we're testing, line 20, is sandwiched between setting the time to 0 and then printing the time after the loop executes. So if we run that, we'll find it actually takes a little bit more than 1 second to execute a loop from 1 to 1000. I just noticed I spaced some of that, but not all of it. There's that more readable. We'll try running that again. It shouldn't affect the time. Okay, so that's 1.03 seconds. Rule of thumb is for every 1,000 counts, it's about a delay of 1 second. You can try that with 2,000 and run that. So pretty close. What was it? For a 5-second delay, 4740. I was trying this a bit. Pretty close to 5 seconds. There's also a little bit of overhead so that smaller weights require relatively longer delays. It's not quite linear, it's a little bit exponential. Anyhow, that may be good enough. Hi, it's Robin from the future, where we have super CPU accelerators plugged into our computers. Right now, it's actually just running at 1 megahertz like a stock C64, but I'll talk about that in a moment. But while editing the video, I was unhappy that I hadn't tried to more precisely hit 1 second with these for next loops. So I'll show you my attempt at making kind of a formula that handles the sort of exponential nature of it. It's far from perfect, but maybe one of you can pick this up and give it a try. So here's my little test rig for it. We're going to loop from 1 to 10. And for each loop, we're going to set TI string to 0. And then this is the line that we're benchmarking for I equals 1 to 947, a little less than 1,000, times x, which is the number of seconds that we want to pause, to the power of 0.99. This is just to scale it down slightly as the time gets bigger. Both of these numbers I mostly arrived at through trial and error, and this is about the best I could come up with. As usual, I'm showing you something and hoping that one of you can improve upon it. And then line 40 just gets the length of time it actually took. And then in a terrible attempt to make the formatting a little prettier, this is just to round it and show the percentage of difference. Okay, enough of that. Let's just try to run it. So the leftmost column is the percentage error. The second column is the target number of seconds, and the third column is the actual time that my scaled for next loop is taking. So it starts off at 1 is perfect, and 6 seconds is perfect, and it curves a bit up to 1.1% error, and then it also starts to curve down. It's actually a negative number, but I had used the absolute function. For these last numbers, so you see that 6 is also perfect. and then it starts to get away a bit. So 0.7%, 1%, and the final is 10 seconds. So each of these takes a little bit longer. And after 10 seconds, my formula really starts to get too large. Like the numbers start to get bigger than they should. But it's pretty close to within 1% error from values 1 through 9. And then it starts to go up into the 2 and 3% errors. So maybe that's helpful. I hope that's not more confusing than it needs to be. You can just use multiples of 1,000, where each 1,000 is a second, or you can scale it up, or you could even use this 950 and multiply that by 2, 3, 4 seconds, and get an okay value. But adding this exponent makes it curve a little bit nicer and track better, at least up to about a 10-second delay. Again, feel free to experiment. So these 4 next loops are nice and simple. Well, at least until I confused it with this. One disadvantage they have is that they're dependent on the CPU speed. So now to my super CPU, I'll switch it up to 20 megahertz. And now, if we run, you can see how much faster it executes at 20 megahertz. According to the numbers here, it's running about 700% too fast, where a 1 second delay is only taking 0.116 seconds. So I know the super CPU is extremely rare, but devices like the Ultimate 64 have become fairly common, the Ultimate 1541, Turbo Chameleon, they all have their own methods of boosting CPU speed as well. So it's something you might want to keep in mind. You're the programmer, your call. If you're wondering why it's only about 700% faster, that's because I don't have any of the optimization modes switched on right now. So the super CPU is switching down to 1 megahertz more often than it needs to sync up with the C64. I've described that in other videos about the super CPU. We're not going to get into that now. Hi, it's Robin from the future, where we don't even need hands to operate our computers anymore. But we still like the sound of keystrokes. My patron, Dr. Craig S. Bruce, asked, why wouldn't a tight for loop take linear time? So here I've modified the previous program, line 30, instead of using the exponent function, just to use linear time, sort of use like a base time for 1 second, and then a slightly smaller amount for every second thereafter. And this is basically an attempt to cover any setup time for the for next loop, and then basically linear time afterwards. Let's see what happens. Again, I just picked those numbers kind of, not really at random, but trial and error. So we'll see here, the second column is the number of seconds it's attempting to count, and then the right-hand column is the actual. And again, on the left is the percentage difference. So you see that it's not, even here, it's not really linear. You'd expect it to be getting closer, like a consistent 1 second there. It's a bit more than a second again. That was for 7 seconds. A bit more again, exactly 9 seconds. And for the final 10 seconds. So you've got here a bit more than a second between these ones. Here, more than a second. But here you've got less than a second between 2 and 3. So even when we have this equation here, we're still not getting a completely linear delay from these tight for next loops. Dr. Bruce suggested perhaps it's because the floating point math that is used in these for next loops requires extra shifting to add 1 to higher values. So I made a little demonstration program for that here. So to test this, I'm counting from 1 to 1,000, and for each time through the loop, we're going to do a loop that just counts 1,000 times just to add 1 to whatever the current x is. So the first time through the loop, he'll just add 1 plus 1, 1 plus 1, 1 plus 1, 1,000 times, not even totaling them up, just to give us a longer number of calculations to make it easier to time. And then the next time through the loop, it'll be 2 plus 1, 3 plus 1, 4 plus 1, and so on. So let's just run it and see what happens. Okay, so 3.716 seconds. So there, 3.76 seconds for 2, 3.8. Sorry about the formatting. It'll be kind of funny when it's a cleaner decimal number. But basically, it's taking either the same length of time here, there, and it went up again, 3.85, 3.86, up again, and now it should stay the same. And basically, every time it reaches or is at the threshold of a new power of 2 for the X column, the delay goes up a little bit longer. So the next time it delays should be at 15. Okay, so that's all the same. Here comes 15. It should go up. Yep, 3.9. And it should go up again for 16. There we go. And now the left-hand column should stay the same until the next power of 2, which will be 31, 32. Okay, so we're not going to get into a full discussion of this, but basically the way that floating point numbers are stored is you have a normalized mantissa, and then it's to a binary power. So when you want to add 1 to another floating number, the 1 has to be normalized to match the bigger number, and that calculation cannot be done in a consistent time. It takes, the bigger the number, the more shifting has to be done. So yeah, I think Dr. Bruce is right that it is not linear time because of the floating point math that is used in a 4NX loop. Sometimes I should really do a video about floating point math, but first I'll have to fully understand it. So another technique we can use is to take advantage of this TI more directly. T equals TI plus 60. So what we're doing is taking the current time in jiffies, adding 60 to it, and storing it in a variable named t. And then for line 30, we'll check if ti is less than t, then we'll go to 30. So this loop will just wait until ti catches up to t. So basically that should wait 1 second. We'll list it. I just realized I also didn't put a space in there. Let's run it and see how long it really takes. Okay, so a little bit more than a second. We can try that with 59 instead. Run. Pretty close. Can probably run it multiple times and we might not get the exact same. There we go. We got exactly 1 that time. There's always going to be a little bit of variation because when you type run, it might be a varying amount of time since the system interrupt last ran, and that can throw up to a 60th of a second of error into the value. Another advantage here is that we don't actually have to reset the timer. We're doing it for our benchmarking, but instead we could just print out the current value of TI divided by 60, and then after the pause, print it out again. So this way we're not messing with the timer, and we can still see how accurate we are. So there you go, exactly 1 second between the two. Let's run it again. Once again, exactly a second. It's actually working really well. So that's probably the best solution. Of course, it doesn't take the parameter in seconds. It takes it in jiffies, 60ths of a second, and you do have to tweak it a little bit. Hi, Robin from the future again. Just checking in with my super CPU with this TI method. I've got it again in 1 megahertz mode. You see I'm getting the same 1 second delay. Now if I switch it up to 20 megahertz and run, it's really close to a 1 second delay, slightly less. If I change the delay to a full 60 and run, now it's exactly a second. So what's happening is that same reason that stock C64, we had to drop this down to 59. That was because BASIC was running a little too slow with this overhead to actually have exactly a 1 second delay between these two print TI statements. But at 20 megahertz, BASIC is fast enough that that delay is negligible and we get exactly a 1 second delay. The bottom line is, if you use the TI method, it's much more CPU accelerator compatible. If you want a 1 second delay, you'll more or less get the same result, both on a stock 64 or with an accelerator. Now note that's different than warp mode in Vice, which speeds up the whole emulation, including reading the keyboard and so on. You may notice in the Vice emulator, if you put it in warp mode, even the cursor starts flashing crazy fast. Repeating keys like the cursor keys become uncontrollable. That's not true with an accelerator on a real C64. The cursor continues to flash at the same speed. There's more processing power, but the system interrupts still run 60 times a second. Hi, it's Robin from the future again. My patron Emily pointed out a problem with this technique. Once every 24 hours, there's a chance of an endless loop happening. So here's a very short program where I've set TI to 2 seconds before midnight, so to speak, before it wraps around. And then we're just going to print TI, the number of jiffies since midnight, in a loop. And just watch what happens. It's a big number of jiffies, and then it wraps around to a small number. We'll just do that again, and I'll stop it once it wraps around. So the largest number it displays is 5,183,998. Actually, if we ran that a couple times, we'd probably get slightly different number. Oh, there we go. 5,184,000. So that's the largest number that TI will be, and that wraps back around to 0. Again, some numbers are missing here just because BASIC isn't quite fast enough to keep up with the changing clock. So where does this large number come from? Well, it's the number of hours times the number of minutes times the number of seconds times the number of jiffies, 60ths of a second. There you go, exactly the same number. Okay, so here I've got another program here where I'm setting the time clock to just 1 second before it wraps around. And we'll do that technique where we just take the current TI, add 60 for a 1 second delay, and then wait for it. And if I run that, it waited 1 second, and then it exited as it should. But you'll notice this is the maximum number possible. I timed that exactly as close as I could. Now, if I just wanted to wait just a tiny bit longer, like 61 jiffies, and I run that, it prints the first value, and it goes into an endless loop. So we could, I think, wait forever, and it will never exit that delay. And if I print, what time is it waiting for? Well, you see here, it's waiting for 5,184,001, a number that TI will never equal. So that's the bug, is that if you're right near the end of the TI clock, then this technique is buggy. So probably the easiest fix for that is just to reset TI string anytime you use it. But if you don't like that idea, you could also do this. After you set it, you can check if T is greater than 518,3999, just to give it a little bit more wiggle room, I'm going one number less. Then we can set T back to 0. But the disadvantage of that, let's try that, is that it more or less immediately exits the delay, so it won't delay the proper length of time, once in every 24 hours, all things being equal. I actually couldn't come up with a perfect solution for this. You might think you could subtract, then T equals T minus 518,3999. And we'll run that, but still immediately exits the loop. because whether you just reset t back to 0 or subtract the amount, thinking like it'd be nice to do a delta time, you'll still cause this to not be true and to exit. This is similar to an integer overflow problem, which usually can be resolved by doing a delta time, but that's when you're using unsigned integers, like in a language like C, they will overflow consistently. And if you do delta time math, where you're subtracting one number from another, they'll all overflow together and you'll end up with the difference that you want. But that's not true in this case, where TI is kind of artificially wrapped back to 0, and your other variables are floats that will scale up a lot more. They won't just wrap around, they'll actually overflow with an error. So anyway, if anybody has a good fix for this that fixes the wraparound problem and still allows for the proper length of delay, please post a comment. One last method is to use the strange wait command. So we'll run it and then we'll talk about it. Okay, so that's a little bit over a second. Not too bad. It's actually a very strange command, and it's only been the last couple years I've even kind of known how it works. And it was actually just in preparation to make this video that I really looked into what the wait command does. The first parameter is the memory location that you want BASIC to monitor to wait upon. So in this case, we're waiting on location 162, which is a 0-page location that the C64 kernel updates. It's the number of jiffies currently. I just add a line here. If I go print peak 162 and go to 5, just a tight loop, you'll see that it just keeps continually counting up. It counts up to 255 and then goes back to 0 again. Actually, it's doing it a little bit faster than BASIC can keep up, but you're getting the idea there. So location 162 is the low byte of the timer. 161 is the middle byte. So if we run that, you'll see it just counts up every whatever that is, about 4 seconds. It'll go up to the next byte, because meanwhile, the low byte is counting from 0 to 255. Every time it reaches the maximum, this one goes up. Actually, why don't I just show that? Okay, so now we're printing the two values side by side. There'll be a space in between. You can see how that low byte keeps counting up, and every time it hits 255, it wraps around, and the middle byte goes up by 1. And we might as well look at the high byte. It'd be many minutes for that high byte to change at all. Okay, that was just to get a little bit of insight as to what's going on inside the kernel. Those bytes are just being updated as part of the kernel system interrupt that reads the keyboard and updates that timer. So what the wait command does is waits for location 162, 2 to the power of 6 is 64. So if we view that location in binary, it's going to start 0, goes 1, 2, 3, all the way up, and eventually it equals 64, and this is what it'll look like at that time in binary. And this line will just sit there and wait and monitor that location until bit 64 is true, and then it will continue on. So that's 64 jiffies. That's why it takes a little bit longer than a second to run. So you might ask, why not just change this to 60 and it'll wait for exactly a second? Well, let's try running that. Well, no, we get a tiny fraction of a second, actually. Why is that? Well, it's because of the quirky way that wait actually works. 60 in binary is actually 32 plus 16 is 48 plus 8 is 56 plus 4 is 60. That's what it looks like in binary. Because of how this wait command works, it waits for any of these bits to be true. It essentially peaks location 162, does a logical AND with this value, and as soon as it's non-zero, it's done waiting and moves on. So what really happens is that with this timer that's counting up from 0, 1, 2, 3, 4, as soon as this bit is true, I guess I wasn't thinking of this turning into a binary lesson, but just in case this isn't clear to you guys, I'm writing these numbers down. 32, 16, 8, 4, 2, 1. This is the value of each of those bits. This bit has a value of 1. This bit has a value of 2, 4, 8. That reads 16. I put them vertically. 32. So all that together is equal to 32 plus 16 plus 8 plus 4 equals 60. So as soon as that timer counts up to 4, then one of these bits will be true and the wait will be done. So we can confirm that if I change the 60 into a 4 and run it, you'll see we got the same value, 0.06666, and that is 4/60ths. Yep, there we go. So that delay is because it's only waiting 4/60ths of a second, because just one of the bits is true. So that makes wait not as useful as I might like. Okay, so the short answer is if you want to wait a second, you'll have to do a little bit more. Any of the binary values will work. You could wait for 32/60ths. So that's a little more than half a second, and so on. But I mentioned this on Twitter, and Hugo Vangelen suggested that you could actually break it up. This is kind of crazy, but he's right. You could wait for 32, then you could wait for 16. Basically, you can wait for each bit in descending order, 162, 8, and then wait for 162, 4. Let's list that. So you can wait for the 32 to happen, then you can wait for the 16, for the 8, the 4. You can split up like that. Let's see if it works. Look at that. Exactly 1 second. It's terrible, but it works. So that's an option. So I suppose you could wait any amount of time as long as you split it up into the proper bits, waiting one at a time. So 2 seconds would be 120 jiffies. So to break that into binary, 120 has a 64 in it. 56 has a 32 in it. 24 has a 16 in it. Sorry, just getting rid of all that. That's ugly. And an 8. So we should be able to, again, do that in descending order. 64, 32, 16, and 8. Those sum up to 120. Let's see if we get exactly 2 out of this. Yes. That very well may be the most precise way of waiting in BASIC, and yet that's pretty terrible. Probably using the TI busy loop, the second way I showed, is the best general purpose way. But I guess they all have a little bit of strength and weakness to them. The for loop, just for simplicity, the TI loop for CPU compatibility and decent simplicity, and then the wait for the best precision. And yeah, it's the most cryptic to use. Hi, it's Robin from the future. One last time, my patron Jarno Mielikäinen suggested doing this. How about poking the value at 162 in this way? So if you want to delay 60, set it to 60 less than 128, and then wait for 128. And if we run, you see that does do exactly a 1 second delay. And we could even make this number bigger if we wanted, like say we wanted a 90 jiffy delay. There you go, that's exactly 1.5 seconds between the two. So this would allow for up to 2 second delays using the wait technique. And while it does disrupt the time clock slightly, it's just doing it to the low byte instead of resetting the whole thing. So it's only throwing time off by about 4 seconds at the most. I think on average, it would actually do less than that. So that's kind of a neat idea, and it seems to work really well. So thanks, Jarno. Okay, so thanks to grymmjack for the question. I hope that helps. Thank you to all my patrons for their support, and thank you for watching. We'll talk to you next time.